Hello everyone. We are almost towards the end of the semester and let's talk about chapter 13. It's about the properties of mixtures, solutions and colloids, and it is a very short chapter. Okay, so in this section we're going to learn about types of solutions, intermolecular forces and solubility, intermolecular forces and biological macromolecules, why substances dissolve, breaking down the solution process, solubility as an equilibrium process, and concentration terms. Solutions and colloids. We know what is a solution, which is a homogeneous mixture and exists as a single phase. Just like maybe you are drinking a Coke, or maybe you are drinking Pepsi, or maybe you are drinking tea without the leaves, or coffee. So they are all homogeneous mixture. Everything exists as a single phase. There could be some particles soluble, but you cannot see the particles. Okay. The particles in a solution are individual atoms, ions, or small molecules. They could be completely soluble in your mixture. A colloid, in other words, which is a heterogeneous mixture and exists as two or more phases which may be visibly distinct. Can you give me an example of a heterogeneous mixture? What are some of the examples? Water and sand, right? And your salad dressing, right? You can see which is a heterogeneous mixture. You have oil as well as water in it. They are not going to be mixed completely, so you can visibly see the phases. Yeah, the particles in a colloid are typically macromolecules or aggregations of small molecules. Solutions and solubility. A solute normally dissolve in a solvent to form a solution. So when we have a solution, what do we have in a solution? Which is a solute and a solvent. Okay, usually the solvent is the most abundant component. You can have little bit of solute in a solvent, bigger amount. Most of the time we use water as a solvent, but in some cases we use organic solvents too. Okay, the solubility, we given the symbol S, of a solute is the maximum amount that dissolves in a fixed quantity of solvent at a given temperature. We call that as the solubility. Okay, sometimes if you Google something, you can find out what is the solubility of calcium carbonate in water. So what that solubility means is the maximum amount that dissolves in a fixed quantity of solvent at a given temperature. And with the temperature, solubility increases. Let's say you want to dissolve sugar in water. Sugar, we all know sugar dissolves in water, but if you heat it, or you have hot water, or you put sugar into your tea when it is hot, it will dissolve faster. But if you are trying to drink iced tea, you want to put some sugar into it, you will see that it will take some time for it to dissolve. Okay, so we have to say what is the temperature that we talk about in a given solubility. Substances that exhibit similar types of intermolecular force dissolve in each other. Substances that exhibit similar types of intermolecular forces. Like if your solvent has dipole-dipole interactions, and then if your solute also have dipole-dipole interactions, they have similar types of intermolecular forces, so they dissolve fast. If you look oil and water, they don't dissolve because they don't have similar types of intermolecular forces. Water has hydrogen bonding. Water also has a dipole, oxygen and hydrogen. And also it has van der Waal. Remember we learned in General Chemistry 1, all substances has van der Waal forces. But if you take oil, oil mainly has van der Waal interactions, van der Waal forces. Okay, so those two doesn't mix with each other because they have different intermolecular forces. This is often expressed by saying like dissolves in like, meaning if you have the same type of intermolecular forces in your solute and the solvent, they dissolve each other. So these are types of intermolecular forces in solutions. Excuse me. We have learned about these intermolecular interactions in detail in General Chemistry 1. But here we can refresh our mind, and this is the first one is called iron dipole. Iron dipole exists if you put sodium chloride, which is your table salt, you put it into water, it dissolves. So sodium chloride is ionic substance. Sodium has a positive charge and chloride has negative charge, right? So iron part coming from your sodium. And then the dipole, water molecule has a dipole because oxygen is electronegative and two hydrogens are electropositive. So there is a dipole interaction in the water molecule. So they are ionic in nature in the sense the dipole means there is a charge distribution, uneven charge distribution. So the oxygen side of the water molecule will be negative in charge, negative all of these, and sodium is positive. So the sodium ion will be surrounded by water molecules facing oxygen end of the water molecule. So this type of interaction we call ion and dipole interaction. Okay, and then so ion dipole interaction has energy 40 to 600. I believe it's kilojoules per mole in terms of unit. Okay, and then we have hydrogen bonding. Hydrogen bonding, you remember hydrogen bonding takes place when hydrogen is bonded to oxygen, nitrogen or fluorine, highly dense small atoms. In water, hydrogen is connected to oxygen. So water can have hydrogen bonding. And in methanol molecular structure is formula CH3OH. These three hydrogens right next to carbon is bonded to carbon. But this hydrogen next to the oxygen bond to oxygen. So methanol is soluble in water because this oxygen and hydrogen can participate in hydrogen bonding with the water molecule. So this is the hydrogen of the methanol can form a hydrogen bond with oxygen of the water. And oxygen also has hydrogen on it, right? So that type of interaction is called hydrogen bonding. Ethanol, remember ethanol is what we find in all types of alcohol that people consume. That also has C2H5OH. If you put alcohol, ethanol, into water, or you try to put into Pepsi or something, you will see that they are soluble. You don't see two layers, meaning the way that they are going to interact or they're going to dissolve with each other is through the hydrogen bonding. Like dissolves like. Okay. Another type of intermolecular interaction is dipole-dipole. One molecule have a dipole like ethanal. Ethanal is an aldehyde and chloroform CHCl3. In chloroform molecule look like that. You have hydrogen, one hydrogen is there, and then there are three chlorines, CHCl3. And you can also have ethanol molecule is CH3, there are three hydrogens and COH. Okay, so the dipole. So this ethanol molecule has a dipole because there is a difference in charge distribution. Oxygen is electronegative. So if you draw the dipole, the arrow would point towards oxygen and this side would be positive. Delta negative, delta positive. And similarly, chloroform, these chlorides are all more electronegative compared to the carbon end. So as a result, this would be arrowhead is pointing towards more electronegative side and this would be positive side. So the dipole is the charge interaction between the two opposite charges between two molecules. So ethanol and chloroform are going to be soluble because they have dipole-dipole interactions. Okay. And another one is iron and induced dipole. You have chloride. Chloride is an ion. And hexane is C6H14. It has only carbon and hydrogens, nothing else. So carbon and hydrogen bonds are non-polar. Because they are non-polar, their charges are not distributed. So you don't have a dipole. But the chloride, when it comes closer to the hexane molecule, it can induce a dipole in the hexane molecule. Because this guy is negatively charged, it comes closer. So since we know that the negative charges are trying to pull electron towards itself, it creates a charge imbalance in the hexane molecule. But that happened due to the chloride. So since chloride is doing that, we call it as an induced dipole, not a permanent dipole like the previous ethanol or the chloroform. Okay, so iron induced dipole is another type of intermolecular interaction that's about 3 to 15 in energy. That is less compared to the dipole-dipole. Another one would be dipole and an induced dipole interaction. Now the xenon is a noble gas. It doesn't have any charge distribution in it. It's just a xenon molecule. And then a water molecule come closer. Water molecule has dipole interaction. Dipole is due to the oxygen being electronegative and the hydrogen end being electropositive. Water molecule has a dipole. But the xenon doesn't have ion or a dipole or a hydrogen bond or nothing. It just only has van der Waals interactions. So the dipole of the water induces a dipole in the xenon. So we call that as dipole-induced dipole interaction. Okay. That's going to be less energy compared to the ion-induced dipole. And then the last one is the dispersion, which is the weakest type of interaction, but it exists in any kind of molecule. Even the previous ones that we talk about, dipole-induced dipole, ion-induced dipole-dipole or hydrogen bond ion dipole, all of these also have dispersion forces, London dispersion forces or the van der Waals dispersion forces. Okay, I've been telling van der Waals, another name for that is the dispersion. They are the same. So the dispersion interactions are it can happen in any molecule like this. Okay, they are very weak. So that's why if you have organic solvent, you will see it evaporates really fast because weaker interactions, they can break the molecules easily away from each other and it can evaporate. Whereas if you put a water about the same amount, even though we know that the water evaporates after a long time, but you will see the organic solvent evaporate a very higher rate. If you put the same amount in about the same time, you will see a big reduction in the organic solvent compared to the water. Okay, dispersion forces that exist in all kinds of molecules. Okay, solutions and intermolecular forces. When a solution forms, what happened? Solute-solute interactions and solvent-solvent attractions are replaced by solute solvent attractions. Okay, when a solution forms, what happened? Before you mix the two things together, there are certain interactions between solute and solvent, and they are going to be replaced by the solute solvent attractions. This can only occur if the forces within the solute and solvent are similar to the forces that replace them. Okay, meaning solute and solvent and solute-solvent should have similar intermolecular interactions. If they don't have it, then they will not mix. Hydration shells around a sodium ion. Earlier also we looked at the sodium. So you can see this is the sodium ion, positively charged. And the water molecules are going to be surrounding the sodium ion. Okay, how do they do that? That is the ion dipole force. Ion is the sodium, dipole coming from the water molecule, and this is the oxygen. The big one is the oxygen, two small ones are the hydrogen. So these are the ion dipole interactions, and then all of these water molecules are also connected to each other through hydrogen bonds. So surrounding the sodium there is a hydration shell. Dual polarity and effects on solubility. Alcohols are organic compounds that have dual polarity. The general formula for alcohol is you can have some carbon hydrogen chain, and then at the end you will see the functional group OH. Remember we learned about the functional groups. So OH is the alcohol functional group. The OH group of an alcohol is polar because oxygen is more electronegative compared to the hydrogen. So OH group is polar. It interacts with water through hydrogen bonds and with hexane through weak dipole-induced dipole forces. We started this talking about the dual polarity. So one side is hydroxyl group alcohol. Alcohol can be dissolved in water through the hydrogen bonds. Because this OH also has hydrogen bonds, water also has hydrogen bonds. And hexane is an organic molecule which is C6H14. It only has carbon and hydrogens. Alcohol and hexane also mix through weak dipole and induced dipole forces because alcohol can also have a dipole in addition to the hydrogen bonding. Okay. Now that is the polar end. That happens through the polar end of the alcohol. Hydrocarbon portion is non-polar. Now the hydrocarbon portion is this part where you have hydrogens connected to the carbon, this hydrogen on carbon. We call that as the hydrocarbon. Remember they only have carbon and hydrogen which is non-polar. It interacts through weak dipole-induced dipole forces with water. Okay, since it's not polar, it interacts with water through weak dipole-induced dipole forces with water. So the water has dipole and the water can induce a dipole in the hydrocarbon portion of the alcohol molecule and through dispersion forces with hexane. And when it reacts with hexane, it also reacts through dispersion forces because it exists in all kinds of molecules, and hexane can only have dispersion forces. So that is the dual polarity of alcohol and how it affects solubility. Okay. Excuse me. Solubility of a series of alcohols in water and in hexane. Alcohol, these are the alcohols: methanol, ethanol, propanol, butanol, pentanol, hexanol. What's happening? in this series, you can see each alcohol increases the carbon number by 1 and hydrogens accordingly. CH3OH, CH3, CH2OH. Now this has 2 more CH2 groups, 3 more, 4 more, 5 more. You can see nothing happened to the OH, which is the polar side of the molecule. What happened to the hydrocarbon? Hydrocarbon side increases, right? So as a result, we will see as you go down this series, the solubility of alcohol in water will decrease, but it will increase the solubility in organic solvents because it increases the hydrocarbon portion. Now methanol, ethanol, propanol, solubility in water infinite. They dissolve. You can put them together and then they become one phase. In terms of solubility in hexane, methanol, since it has a very small hydrocarbon portion, 1.2. But ethanol and beyond, all of these are going to be soluble in hexane because the hydrocarbon part increases. But in terms of water, you will see the solubility decreases as the hydrocarbon part increases. The polar side remains the same. There is nothing to increase the polarity. It's the same thing. Okay. Predict which solvent will dissolve more of this given solute. You have sodium chloride in methanol or in 1-propanol. Predict which solvent will dissolve more of the given solute. Is it going to be sodium chloride in methanol will dissolve well or sodium chloride in propanol? What do you guys think? Sodium chloride is an ionic substance. What do we have in methanol? We have methanol, we have excuse me, dipole. Excuse me. And also between methanol has hydrogen bonds, but the sodium chloride doesn't have hydrogen bonds. And in propanol, you have a little bit bigger hydrocarbon part compared to the methanol. So sodium chloride is ionic and it dissolves well in polar solvents through ion dipole forces. Remember, we saw in water and sodium is an ion, water was a dipole. So similarly, this also has a dipole, and this dipole is bigger compared to this one because smaller hydrocarbon here. Okay, so methanol and propanol have a polar hydroxyl group OH. But the hydrocarbon portion of each alcohol interacts only weakly with ions, these parts. Okay, and this one has a longer hydrocarbon portion compared to the methanol, so it would dissolve well in methanol. Okay, and then ethylene glycol. This is ethylene glycol. There are 2 hydroxyl groups. Is it going to soluble in hexane better, or is it going to, so this is the hexane, or in water? What do you guys think? This has 2 OH groups. Is it going to dissolve well in hexane or in water? Remember, all of the substances has dispersion forces. But the ethylene glycol also has hydrogen bonding because it has hydrogen on oxygen. Okay. Also, it has dipole interactions. Water also has hydrogen bonds and dipole. So these two will dissolve well with each other compared to hexane. Okay. The last one, diethyl ether. This is diethyl ether in water or in ethanol. Diethyl ether, there is an oxygen, but there are no hydrogen bonds because this oxygen is connected to 2 carbons. Okay. So this, since there is an oxygen, it has a dipole, but that dipole is simple and also it has dispersion forces. Okay. This can form hydrogen bonds to water or to ethanol, But ethanol can also interact well with diethyl ether through dispersion forces. So as a result, diethyl ether will dissolve well in ethanol, okay, than in water. We in fact will see two layers when you put water into a diethyl ether, but when you put alcohol and ether together, we will not see any separation of the phases. And you can also see the explanations that I just gave you here. For ethanol, diethyl ether molecules interact through simple, not dimple, simple dipole and dispersion forces. They can form hydrogen bonds to water or to ethanol. However, ethanol can also interact with the ether effectively through dispersion forces because it has a hydrocarbon chain. So diethyl ether will dissolve well in ethanol than the water. Okay. Intermolecular forces and biological macromolecules. Intermolecular forces play a key role in determining the structure and function of biological molecules. There are two key groups of interactions to note. Polar and ionic groups attract water, but non-polar groups do not. Distant groups on the same molecule attract each other in the same way that groups on different molecules do. Okay. Let's look at a structure of amino acid. This is the charged form of amino acid under physiological conditions. So you have a carbon for every amino acid. It has amine group and also it has a carboxylate group, and you can have a side chain R group, and also this carbon carries a hydrogen. Only thing that is going to differ is the side chain, one of 20 different side chains. Okay, we call this as the alpha carbon because it's next to the carbonyl group, alpha carbon. Amino acids can be classified by their side chains. So you will see some of these are non-polar amino acids because the R group that we saw in the previous slide, you can see this is a hydrocarbon with carbon and hydrogens. So this is non-polar. There is no polarity. It has a non-polar side chain. So that makes this leucine a non-polar amino acid. And then the serine and cysteine have a polar side chain, CH2OH, CH2SH. This is a thiol, this is an alcohol. So they are called polar amino acids. And then the lysine and glutamic acid, you can see there are charged groups, ammonium group or carboxylate. So these are ionic side chains. Okay. Forces that maintain protein structure. So this is the big protein that you are seeing here. You will see some of the intermolecular interactions that we talked about. Let's see what we can see. Hydrogen bonds with polypeptide chains. So these ones are hydrogen bonds in the polypeptide chains. So these ones, they are hydrogen bonds. Region where dispersion forces predominate. Over here, only dispersion forces. Meaning this is all hydrophobic. They repel water. Only has dispersion forces. Okay. And then you can also see some salt links. How do we form a salt? Salts are formed between positive ion and a negative ion. Like the sodium chloride is a salt, Na plus Cl minus. So here you have a negative charge, here you have a positive charge. So that's a salt link, ionic interaction right there. Also you can see some molecules are forming hydrogen bonds. And then the disulfide bridges, bonds between two sulfur atoms. Again, these are hydrogen bonds. Wherever you see these pink bonds, they are hydrogen bonds. Hydrogen bonds. And then you will also see iron dipole forces. There is a iron and then a dipole from the water and the iron here, like a carboxylate ion. Another iron and dipole force. Okay. So this is the folding of the protein. Maybe you have heard about the protein folding, the tertiary structure of the protein. So the hydrophobic side is this. Hydrophilic means water loving side. Hydrophobic and hydrophilic. Okay. Excuse me. The cleaning ability of a soap depends on the dual polarity of its molecules. Remember, we talk about the dual polarity in alcohol. Alcohol has a OH polar side and a non-polar hydrocarbon side. So the soap also has that dual polarity. One side is polar, the other side is non-polar. That helps soap or the detergents that we use in a daily basis to clean even the clothes or the greasy stuff that we eat, cleaning your plates and cleaning your hands and all that. So in a soap molecule, you will see a polar head, polar molecules. Polar head of soap molecules interact with water molecules, right? Water molecules. And if you eat some greasy stuff, we know you put water into it, the water will just float over it, right? But when you put detergent, it will go away. That's because in the detergent has this hydrophobic or the dispersion forces part, where the similar interaction you find in your greasy food or the oil-based food. So that helps to clean up that part because they have similar intermolecular interactions. Non-polar tails of soap molecules interact with hydrocarbons in a grease stain. Non-polar molecules make up a grease stain. Okay, so that's how the detergents and your soap cleans greasy stuff as well as non-greasy stuff because it has polar head and a non-polar tail. A membrane phospholipid also has two polarities, dual polarity. Polar ionic head and non-polar tail. Looks like a figure, right? Yeah. And then the double helix of DNA. We know the DNA is two strands, right? But they are like two, we all have seen how it looks like this, right? Excuse me. Excuse me. So it also has a polar ionic exterior and non-polar interior. It's non-polar. And then you will also see iron dipole forces, hydrogen bonds existing in the double helix. The formation of this double helix between the two strands, they are connected through hydrogen bonds. You see, hydrogen bonds between the bases make the structure that we see for the DNA molecule, double helix. Maybe we'll stop here and start the second session in a second video.